Earth is 4.5 billion years old. That's so much time our brain can't really understand it. Modern humans have existed for only 300,000 years, and our technological civilization is less than 200 years old. This means we've used only 0.000004% of Earth's history. But here's what keeps scientists awake at night. We have 4.5 billion years of our planet's history, about which we know almost nothing. The Silurian hypothesis suggests something incredible. There could have been an entire civilization of intelligent beings millions of years before us, and we would never know. Think about it. If all humans disappeared today, in 10 million years, almost nothing would remain. Our cities would turn to dust. Our cars and computers would completely disappear. Even the changes we made to the climate would be just a small mark in the rocks. So the big question is, how many times has intelligent life appeared and disappeared on Earth without leaving traces we can see? Subscribe to the channel, leave your like and comment from which part of the world you're watching. Get comfortable and relax. Let's begin. Hello there, and welcome to this quiet corner where curiosity is allowed to take its time and wonder unfolds without hurry. Tonight, we're stepping into one of the most profound questions our species has ever asked, not about the distant stars or the depths of space, but about our own planet, our own history, and whether we might not be quite as alone in time as we've always assumed. This is the story of the Silurian hypothesis, a scientific thought experiment that asks a simple yet deeply unsettling question. What if we are not the first civilization to rise on Earth? The name comes from a British science fiction series where intelligent reptiles called Silurians ruled the planet long before humans arrived, but the hypothesis itself is far from fiction. It's a serious scientific framework proposed by researchers who wanted to understand something fundamental about our own impact on the planet and whether similar impacts might have occurred before, so long ago that we've simply missed them entirely. When most people think about ancient history, they imagine pharaohs and pyramids, stone circles and buried cities. Even when we reach back to the very dawn of human civilization, we're still only looking at perhaps 10 or 12,000 years. That feels ancient to us, but in the context of Earth's history, it's barely a whisper. Our planet is 4.5 billion years old. For most of that time, there were no humans at all. There weren't even mammals for the vast majority of it. Life spent billions of years in forms we would barely recognize, evolving in oceans, adapting to land, experimenting with intelligence in ways we're only beginning to understand. And that's where the Silurian hypothesis becomes both fascinating and humbling. It doesn't claim that ancient civilizations existed. Instead, it asks a much more careful question. If they had existed, would we be able to detect them? Would the geological record preserve enough evidence for us to recognize that something intelligent had been here before? And if the answer is no, then what does that tell us about our own assumptions regarding the uniqueness of human civilization? To understand why this question matters, you have to think about how planets work over deep time. The Earth is not a static museum that carefully preserves everything that happens on its surface. It's a dynamic, living system that constantly recycles itself. Plate tectonics grind up old seafloor and create new crust. Erosion wears down mountains and fills valleys with sediment. Rivers change course, forests rise and fall, and ice ages come and go, scraping the surface clean and depositing new layers of rock and soil. Most of what has ever existed on Earth has been erased by these processes. The fossil record which we use to understand ancient life is incredibly incomplete. We're lucky to find even fragments of most species that once lived. Entire ecosystems can vanish without leaving a trace that we could recognize millions of years later. If this is true for biological life, which often leaves behind bones, shells, and other hard parts, imagine how much harder it would be to detect the remnants of a technological civilization. Consider what might happen to our own cities if humans disappeared tomorrow. Buildings would crumble within centuries, roads would crack and be overgrown by vegetation. Most of the infrastructure we consider permanent would decay rapidly without maintenance. Even our most durable materials, steel and concrete, would rust and crumble over thousands of years. In the span of geological time, measured in millions or tens of millions of years, almost everything we've built would be ground back into dust. But our civilization would still leave traces, chemical signatures written into the planet's atmosphere, oceans, and soil. We are burning fossil fuels at unprecedented rates, altering the composition of the atmosphere in ways that will be detectable in ice cores and sediment layers for thousands of years. We're producing synthetic materials, plastics, and industrial chemicals that don't occur naturally and persist in the environment long after we're gone. We've even scattered radioactive isotopes from nuclear testing across the globe, creating a distinct signature in the geological record that future scientists might one day discover. The Silurian hypothesis takes these modern signatures and asks whether similar patterns might exist in the deep past. Could an ancient civilization have left behind chemical fingerprints that we've overlooked or misinterpreted? Could changes in atmospheric composition, unusual concentrations of rare metals or synthetic compounds be hiding in plain sight within the geological record, dismissed as natural anomalies because we never thought to look for them as signs of intelligence? This isn't about little green men or ancient astronauts. The hypothesis focuses on terrestrial intelligence, life that evolved here on Earth just as we did, but perhaps millions or hundreds of millions of years earlier. Such a civilization wouldn't need to be human-like. Intelligence can take many forms, and there's no reason to assume that all technological species would follow the same developmental path we have. What makes this question so compelling is how it forces us to confront the limits of our knowledge and our assumptions. Science works by building models of how the world operates, then testing those models against observations. But our models of the deep past are built on the assumption that major changes in the geological record result from natural processes, volcanic eruptions, asteroid impacts, climate shifts driven by orbital changes or solar variations. We don't typically consider intelligence as a potential explanation for ancient anomalies, because we assume intelligence is recent. Yet intelligence isn't necessarily rare. It's emerged at least once on this planet, in us, and there are signs of sophisticated problem-solving abilities in many other species. Dolphins use tools and pass knowledge to their offspring. Octopi solve complex puzzles and modify their environment. Some birds use multi-step reasoning to obtain food. Even social insects like ants and bees coordinate behavior in ways that suggest collective intelligence. If intelligence can emerge once, there's no fundamental reason it couldn't emerge again, perhaps multiple times over Earth's long history. The challenge lies in detection. A civilization that existed 50 million years ago would have faced the same geological recycling that erases most traces of the past. Their cities would be dust, their artifacts scattered or destroyed, their records obliterated by time. But if they used energy on a global scale, if they altered ecosystems, if they produced synthetic materials or changed atmospheric chemistry, some evidence might survive in the right places under the right conditions. This is where the hypothesis becomes a detective story. Instead of looking for obvious artifacts like tools or buildings, researchers would need to search for subtle signatures, unusual spikes in carbon isotopes that might indicate fossil fuel burning, rare earth elements concentrated in ways that suggest industrial processing, synthetic compounds that don't match any known natural process, or rapid changes in biodiversity that can't be explained by climate or geological events alone. Some of these signatures might already exist in the scientific literature, filed away as curiosities or unexplained anomalies. Science tends to focus on phenomena that fit existing theoretical frameworks, and isolated oddities often receive less attention unless they're part of a larger pattern. A chemical spike in one sediment core might be dismissed as contamination or a local event, but if similar spikes appeared globally in sediments of the same age, they might tell a different story. The Silurian hypothesis doesn't prove that ancient civilizations existed. Instead, it provides a framework for thinking about how we might detect them if they did. It's a thought experiment that helps scientists understand both the limits of the geological record and the scope of our own impact on the planet. By imagining how future geologists might study our civilization millions of years from now, we gain insight into what traces of intelligence might look like in deep time. There's also a deeper philosophical dimension to this question. If we're not the first intelligent species to arise on Earth, what does that mean for our understanding of ourselves and our place in the cosmos? Does it make us less special, or does it connect us to a longer, richer history of consciousness and creativity? Are we building on foundations laid by others, or are we repeating patterns that have played out before? These questions don't have easy answers, and they may never be fully resolved. The evidence for ancient civilizations may be too sparse, too ambiguous, or too deeply buried to recover. But the act of asking the question opens up new ways of thinking about time, intelligence, and the relationship between life and geology. It reminds us that Earth's history is vast and largely hidden from us, and that our assumptions about the past may be incomplete. As we continue this exploration, we'll dive deeper into what such evidence might look like, where it might be preserved, and why it's so difficult to distinguish the signatures of intelligence from the background noise of natural processes. We'll examine specific examples of geological anomalies that have puzzled scientists, and consider whether any of them might hint at something more than purely geological origins. Whether or not ancient civilizations existed, the Silurian hypothesis serves an important purpose. It challenges us to think more carefully about our impact on the planet, to consider the impermanence of everything we build, and to remain humble about how much we truly understand regarding the deep history of our world. In a universe where time is measured in billions of years and intelligence may be rarer and more fleeting than we imagine, the possibility that we're not the first becomes both sobering and strangely comforting. The story continues as we delve into the mechanics of deep time, where mountains rise and fall like waves, where the very face of the planet transforms beyond recognition, and where the traces of entire worlds can vanish as completely as if they never existed at all. The Earth keeps its secrets well, but sometimes, if we know how to look, it whispers hints of stories we never expected to hear. The Earth keeps its secrets well, but sometimes, if we know how to look, it whispers hints of stories we never expected to hear. To understand why those whispers are so faint, we need to grasp something that challenges our everyday experience of time. We live in a world where a human lifetime feels substantial, where decades matter, where centuries represent the deepest history we can easily comprehend. But the Earth operates on a completely different timescale. One so vast that our entire species' history becomes little more than a brief flicker. Geologists call this deep time, and it's perhaps the most difficult concept for our minds to truly absorb. When we say the Earth is 4.5 billion years old, the number itself is almost meaningless. We can write it down, we can calculate with it, but we cannot really feel what it means. To get a sense of the scale, imagine that the entire history of our planet was compressed into a single year. On this timeline, human civilization would begin only in the last few seconds before midnight on December 31st. All of recorded history, every empire that has risen and fallen, every monument we've built, every story we've told, would unfold in those final moments. This perspective is crucial because it helps us understand why evidence of ancient civilizations might be so hard to find. We're not just looking back a few thousand years or even a few million years. We're potentially searching across hundreds of millions of years, spans of time during which the Earth has completely transformed itself multiple times over. The continents have drifted to entirely different positions. Mountain ranges have risen from the sea and been worn back down to nothing. Entire ocean basins have opened and closed like vast, slow breathing. During these transformations, the surface of the planet gets recycled in ways that most people never consider. The process starts with erosion, the slow but relentless wearing away of everything exposed to wind, water, and weather. Rain falls on mountains and dissolves minerals from the rocks. Rivers carry this dissolved material downstream, along with particles of sand and silt. Eventually, these sediments settle on the floors of lakes and oceans, where they accumulate in layers over millions of years. But the story doesn't end there. The weight of these accumulating sediments compresses the layers beneath, gradually transforming mud into shale, sand into sandstone, and carbonate into limestone. These sedimentary rocks become the archives of Earth's history, preserving fossils and chemical signatures from ancient environments. However, even these archives are temporary. The rocks themselves can be heated and pressurized until they transform into entirely different types of metamorphic rock, erasing their original structures and the information they contained. Meanwhile, the even deeper processes of plate tectonics ensure that no part of the Earth's surface is truly permanent. The ocean floor, where much of our planet's sedimentary record accumulates, is constantly being created at mid-ocean ridges and destroyed at subduction zones where oceanic plates dive beneath continents. The average age of the ocean floor is only about 200 million years, which means that older seafloor has been entirely recycled back into the Earth's mantle. Any evidence that might have accumulated there has been melted and reprocessed, becoming part of the planet's deep interior rather than its historical record. Even continental surfaces, which are generally more stable than ocean floors, undergo constant change. Glaciers advance and retreat, scraping away entire layers of rock and sediment. Rivers change course, carving new valleys and abandoning old ones. Volcanic activity buries landscapes under lava and ash. Wind redistributes sand and dust across vast distances. The very ground we walk on is in motion, though so slowly that we rarely notice. This constant recycling means that the geological record is full of gaps, periods where no rocks survive from particular time intervals or geographic regions. Scientists call these gaps unconformities, and they represent millions or even hundreds of millions of years of missing history. It's as if someone had taken a library and randomly removed entire sections, leaving only scattered books and torn pages from which to reconstruct the complete story. The implications for detecting ancient civilizations are profound. If a technological species had existed hundreds of millions of years ago, most direct evidence of their presence would likely have been destroyed by these geological processes. Their cities would have crumbled and been buried under sediment. Their roads would have been broken up by earthquakes and weathering. Their artifacts would have been scattered and ground into fragments too small to recognize. But total erasure isn't inevitable. Under specific conditions, traces can survive for enormous periods of time. The key is rapid burial in environments where decay is slowed or prevented entirely. Fossils form when organisms are quickly covered by sediment, protecting them from scavengers and preventing their complete decomposition. Similarly, human artifacts can sometimes survive for thousands of years when preserved in dry caves, frozen tundra, or oxygen-poor underwater environments. The challenge is that preservation requires very particular circumstances, and those circumstances become increasingly rare as we look further back in time. A civilization that existed 50 million years ago would have needed to leave traces in locations that remained geologically stable, avoided erosion, and escaped the recycling of plate tectonics. Such places exist, but they're scattered and limited. Some of the most promising locations for preserving ancient evidence are called cratons, the oldest and most stable parts of continental crust. These regions, found in places like the Canadian Shield, the Australian outback, and parts of Africa, contain rocks that are billions of years old. If any traces of extremely ancient civilizations survived anywhere, it might be in these stable zones. Lakes and inland seas also offer potential preservation sites. When these bodies of water have no outlets, they can accumulate sediments continuously for millions of years without interruption. The layers build up like pages in a book, potentially preserving chemical signatures or unusual materials that might indicate industrial activity. Some of these ancient lake beds have been uplifted and exposed by geological processes, making them accessible to modern researchers. Ice cores from polar regions preserve atmospheric conditions going back hundreds of thousands of years, and in a few rare cases, even longer. These frozen archives contain bubbles of ancient air, dust from volcanic eruptions, and chemical signatures of past climate conditions. They're incredibly detailed records, though they only extend back a tiny fraction of Earth's history. Ocean sediment cores provide another window into the past. Despite the recycling of oceanic crust, some sediments accumulate in deep ocean basins that remain undisturbed for millions of years. These cores can reveal changes in ocean chemistry, temperature, and biological productivity that might reflect global environmental changes caused by industrial activity. But even in these ideal preservation sites, the traces would be subtle. We wouldn't expect to find recognizable machines or structures. Instead, we'd be looking for chemical anomalies, unusual concentrations of rare metals that might indicate mining and refining, synthetic compounds that don't occur naturally, or abrupt changes in atmospheric composition that can't be explained by known geological processes. The search becomes a matter of statistical analysis and pattern recognition. Natural processes can produce almost any chemical signature if you look at enough samples, but they typically do so in patterns that follow physical laws and known mechanisms. Artificial processes might produce signatures that are more random, more concentrated, or more widespread than natural ones would be. This is where the Silurian hypothesis intersects with our understanding of our own impact on the planet. We're currently conducting a planet-wide experiment in atmospheric chemistry, releasing carbon dioxide and other greenhouse gases at rates that will leave clear signatures in the geological record. We're also dispersing synthetic materials, radioactive isotopes, and industrial chemicals across the globe. Future geologists will easily be able to detect our presence even millions of years from now. But our industrial civilization has only existed for a few hundred years, barely an instant in geological time. If it ended tomorrow, the signature we'd leave would be a very thin layer in the sedimentary record, perhaps only a few centimeters thick in most locations. Finding and recognizing such a layer from the distant past would require both luck and careful analysis. The thinness of these potential signatures is one of the key challenges in testing the Silurian hypothesis. Most geological processes operate over thousands or millions of years, creating thick layers of rock that are easy to identify and study. But civilizations might exist for much shorter periods, geologically speaking, leaving only the faintest traces behind. There's also the question of what kind of civilization we might be looking for. Human industrial society is based on burning fossil fuels, mining metals, and producing synthetic materials. But there's no reason to assume that all technological species would follow the same path. An aquatic civilization might develop very different technologies that leave different signatures. A species that evolved in a different atmospheric composition might use different energy sources entirely. Some civilizations might even be deliberately subtle in their environmental impact, having learned from earlier mistakes or evolved in ways that emphasized sustainability over growth. Such societies might leave almost no detectable trace, making them effectively invisible to future archaeologists, no matter how carefully they searched. Despite these challenges, the search for ancient technological signatures continues to intrigue researchers. It's partly an intellectual exercise, a way of thinking about the limits of detection and the assumptions built into our understanding of the past. But it's also a practical concern as we try to understand our own impact on the planet and what kind of legacy we're creating for future generations. The deep time perspective also provides a humbling context for human achievements. Our cities and monuments, which seem so permanent from our limited perspective, are temporary features that will eventually be recycled by geological processes. The mountains we consider eternal are actually quite young in Earth's history, and they too will eventually be worn away. Even our species, which has existed for only a few 100,000 years, is a recent experiment in the grand story of life on Earth. This doesn't diminish the significance of human civilization, but it does place it in a broader context. We are part of a planet-scale system that has been experimenting with complexity and intelligence for billions of years. Whether we're the first to achieve technology or the latest in a long line of civilizations, we're participating in something much larger than ourselves. We are participating in something much larger than ourselves, a planetary story that unfolds across timescales so vast they challenge our ability to comprehend them. And within this story, the question of what might survive becomes not just academic, but deeply practical. Because if we want to understand whether ancient civilizations could have existed, we first need to understand what kinds of traces actually persist through deep time and what forces work to erase them. The process of preservation and destruction operates according to principles that seem almost designed to frustrate future archaeologists. The things that matter most to a civilization, its knowledge, its culture, its daily life, are often the most fragile. Paper burns, wood rots, and digital storage degrades within decades without careful maintenance. Even stone monuments, which we think of as permanent, gradually succumb to weathering and erosion. The Sphinx has lost its nose, the Parthenon its roof, and countless other structures have crumbled into ruins that archaeologists must painstakingly reconstruct from fragments. But some things do survive, and understanding what persists can help us think about what traces an ancient civilization might have left behind. Ceramics, for instance, are remarkably durable. Pottery shards survive in archaeological sites for thousands of years because fired clay is essentially artificial rock, resistant to most forms of decay. Glass also endures well under the right conditions, and both materials could potentially survive for millions of years if buried quickly and protected from mechanical weathering. Metals present a more complex picture. Pure metals like gold are nearly indestructible and can survive indefinitely in the right environment. But most metals used by technological civilizations are alloys that corrode over time, especially in the presence of oxygen and water. Iron rusts, copper oxidizes, and even apparently permanent materials like bronze gradually break down. However, the process isn't uniform. Metals buried in dry, stable environments can persist much longer than those exposed to moisture and temperature changes. The key insight is that preservation depends heavily on local conditions rather than the inherent properties of materials. A plastic bottle thrown into a landfill might decompose within decades, but the same bottle buried in an oxygen-free environment could potentially survive for thousands of years. This variability makes the search for ancient artifacts particularly challenging because it means that evidence might survive in some locations while being completely destroyed in others. Chemical signatures offer perhaps the most promising avenue for detecting ancient civilizations because they can persist even after the original materials have been destroyed. When we burn fossil fuels, we don't just release carbon dioxide into the atmosphere, we also alter the isotopic composition of that carbon in ways that can be detected in ice cores, sediment samples, and even the growth rings of ancient trees. These chemical fingerprints can survive long after the factories and power plants that created them have crumbled into dust. Similarly, mining and refining activities concentrate certain elements in ways that don't occur naturally. A copper mine creates high concentrations of copper and associated elements in soil and groundwater that can persist for thousands of years. Smelting operations produce distinctive slag that contains unusual combinations of metals and minerals. Even relatively simple technologies like agriculture can leave lasting chemical signatures by altering soil composition and nutrient cycles. But perhaps the most intriguing possibility is that some traces of ancient civilizations might be hiding in plain sight, misinterpreted as natural phenomena because we lack the framework to recognize them as artificial. The geological record is full of anomalies, unusual formations, and chemical signatures that don't fit neatly into our current understanding of natural processes. Most of these anomalies undoubtedly have natural explanations that we simply haven't discovered yet. But it's worth asking whether some of them might represent something else entirely. Consider the problem of dating. Most archaeological techniques for determining the age of artifacts work well for materials that are thousands or even tens of thousands of years old. But these methods become increasingly unreliable as we push further back in time. Carbon dating, for instance, is only useful for materials less than about 50,000 years old. For older materials, we rely on techniques like potassium-argon dating or uranium-lead dating, which work on geological timescales but can't distinguish between materials that are 50 million years old and materials that are 51 million years old. This means that if we found an obviously artificial object in a rock formation dated to 100 million years ago, we might not be able to determine whether it was actually that old or whether it had somehow been introduced into the formation more recently. Contamination is a constant concern in geological research, and extraordinary claims require extraordinary evidence. An isolated, anomalous object would likely be dismissed as contamination or misidentification unless it was part of a larger, consistent pattern. The scale of this problem becomes apparent when we consider how much of Earth's surface remains unexplored at the level of detail needed to detect ancient artifacts. The deep ocean covers more than 70% of the planet's surface, and we've examined only a tiny fraction of the seafloor with sufficient resolution to identify small objects. Most land surfaces have been altered by erosion, vegetation, and human development to the point where ancient artifacts would be difficult to detect without extensive excavation. Even when we do find unusual objects or formations, interpretation can be contentious. Natural processes can create surprisingly regular structures that look artificial at first glance. Columnar basalt formations create geometric patterns that resemble constructed walls. Concretions form spherical or cylindrical shapes that can look like manufactured objects. Salt deposits can create crystal formations with perfect geometric angles. Without additional context, it can be difficult to distinguish natural from artificial origins. This interpretive challenge is compounded by the fact that we don't know what ancient technologies might have looked like. Human civilization has followed a particular path from stone tools to metals to electronics, but there's no reason to assume that all intelligent species would follow the same trajectory. An aquatic civilization might develop biotechnology instead of metallurgy. A species with different sensory capabilities might create technologies based on principles we haven't discovered or don't use. The search for ancient technological signatures also raises questions about what we mean by civilization and technology. Our modern understanding tends to focus on industrial processes and manufactured goods, but technology can be much broader than that. Agriculture is a technology that can dramatically alter landscapes and leave lasting traces in soil chemistry and pollen records. Domestication of animals is a technology that can change the evolutionary trajectories of entire species. Even sophisticated understanding of astronomy or mathematics might be considered technological achievements, though they might leave no material traces at all. Some researchers have suggested looking for signatures of genetic engineering or selective breeding that might indicate biological technologies. If an ancient civilization had domesticated plants or animals, or had deliberately altered the genetic makeup of species, those changes might still be detectable in the DNA of modern organisms. This approach has the advantage of looking at the entire biosphere as a potential archaeological site, rather than focusing on specific geological locations. Another intriguing possibility is that ancient civilizations might have left traces in space rather than on Earth's surface. If a species had developed space travel, they might have built structures on the Moon or other bodies in the solar system where geological recycling doesn't occur. The lunar surface preserves impacts and other features for billions of years because there's no atmosphere or water to cause erosion. However, detecting such structures would require much more detailed exploration of the solar system than we've accomplished so far. The question of preservation also depends on how long ancient civilizations might have lasted. Our industrial civilization has existed for only a few hundred years, but there's no reason to assume that all technological species would have such brief histories. A civilization that lasted for millions of years might leave much more extensive traces than one that existed for only a few thousand. On the other hand, a long-lived civilization might also develop more sustainable technologies that left smaller environmental footprints. Climate also plays a crucial role in preservation. Ice ages and other major climate changes can bury or expose archaeological sites, sometimes preserving materials for much longer than would otherwise be possible. The cyclical nature of climate change means that evidence might be hidden for millions of years before being exposed again by erosion or tectonic activity. This suggests that the search for ancient civilizations might require a long-term perspective, continuing to monitor geological processes that might reveal new sites over time. The study of preservation and destruction ultimately reveals the profound challenge facing anyone who wants to detect ancient civilizations. The Earth is remarkably efficient at recycling its surface materials, and the older the evidence, the less likely it is to survive in recognizable form. This doesn't prove that ancient civilizations didn't exist, but it does suggest that proving their existence would be extraordinarily difficult. Yet, the search continues to fascinate researchers because it illuminates fundamental questions about the nature of intelligence, technology, and planetary change. Whether or not we ever find evidence of ancient civilizations, the process of looking helps us understand our own impact on the planet and our place in the long history of life on Earth. The process of looking helps us understand our own impact on the planet and our place in the long history of life on Earth. And it was precisely this perspective that led two scientists, Gavin Schmidt and Adam Frank, to formalize what had been a largely speculative question into a rigorous scientific framework. In 2018, they published a paper that gave the Silurian hypothesis its name and transformed it from science fiction speculation into a legitimate area of research. Schmidt, a climate scientist at NASA's Goddard Institute for Space Studies, and Frank, an astrophysicist at the University of Rochester, weren't setting out to prove that ancient civilizations had existed. Instead, they were interested in a more subtle question. How would we even recognize the signatures of an ancient industrial civilization in the geological record? Their approach was methodical and grounded in what we already know about how modern human activity is changing the planet. The researchers began by cataloging the ways our current civilization is altering Earth's systems. We're changing the composition of the atmosphere by burning fossil fuels, releasing carbon dioxide, methane, and other greenhouse gases at rates unprecedented in recent geological history. We're altering the chemistry of the oceans through acidification and pollution. We're redistributing elements across the planet's surface through mining, agriculture, and industrial processes. We're creating entirely new materials that don't exist in nature, from plastics to synthetic chemicals to radioactive isotopes. All of these changes are being recorded in the geological record as they happen. Ice cores preserve the changing composition of the atmosphere. Ocean sediments capture shifts in marine chemistry. Soil samples reveal the spread of industrial pollutants and synthetic materials. Future geologists studying these layers millions of years from now would easily be able to identify a period of rapid, dramatic change that coincided with the rise of human industrial civilization. But Schmidt and Frank pushed the analysis further. They asked what would happen to these signatures over much longer periods of time. Would they still be detectable after 10 million years, 100 million years? And if similar signatures existed in the deep past, would we recognize them for what they were, or would we interpret them as natural phenomena? This question led them into the complex world of geochemical cycles and biogeochemical signatures. When we burn fossil fuels, we're not just adding carbon dioxide to the atmosphere. We're also changing the isotopic ratios of carbon in ways that reflect the biological origin of the fuels we're burning. Coal and oil were formed from ancient plant and animal matter that had a particular isotopic signature. And when we burn these fuels, we release carbon with that same signature into the modern environment. This isotopic shift is already visible in the geological record. Scientists can detect the beginning of large-scale fossil fuel burning in ice cores and sediment samples by looking for the characteristic change in carbon isotope ratios. The signal is clear and global, a sharp deviation from the natural background that preceded it. Similar shifts might be detectable from ancient civilizations that used biological fuels, though the signatures would depend on what types of fuels they used and how they processed them. The researchers also considered the signatures of large-scale mining and materials processing. Modern industrial civilization concentrates certain elements in ways that rarely occur naturally. We extract metals from widely dispersed ores and concentrate them in specific locations. We create alloys that don't form naturally. We produce pure forms of elements that are usually found only in chemical compounds. All of these activities leave distinctive chemical fingerprints that could potentially survive for millions of years under the right conditions. But perhaps the most intriguing aspect of their analysis was the recognition that many of the signatures we're creating today might be easily mistaken for natural processes if found in ancient rocks. Rapid climate change, ocean acidification, and mass extinction events have occurred many times in Earth's history, driven by volcanic activity asteroid impacts, and other natural causes. The challenge would be distinguishing between natural and artificial causes for such events, especially when the direct evidence of civilization had long since disappeared. This led Schmidt and Frank to focus on what they called short-term events in the geological record. From a human perspective, short-term might mean anything from decades to thousands of years. But from a geological perspective, short-term events are those that occur over periods of less than a few 100,000 years. These events show up as sharp transitions in the rock record, sudden changes in chemical composition or fossil content that indicate something dramatic happened relatively quickly. The researchers identified several such events in Earth's history that have puzzled geologists precisely because they seem to happen too quickly to be explained by the usual slow geological processes. The Paleocene-Eocene thermal maximum, which occurred about 56 million years ago, saw global temperatures rise by 5 to 8 degrees Celsius over a period of less than 20,000 years. The cause is still debated, but it involved massive releases of carbon into the atmosphere and oceans, creating conditions similar to what we're experiencing today through fossil fuel burning. Another example is the Younger Dryas event, a brief return to Ice Age conditions that occurred about 12,800 years ago. This event happened over a period of decades or centuries, far too quickly to be explained by orbital changes or other astronomical cycles. The cause remains uncertain, though most scientists favor explanations involving changes in ocean circulation or freshwater outflows from melting ice sheets. These rapid events share certain characteristics that might be signatures of industrial activity. They happen quickly compared to normal geological processes. They involve global changes in atmospheric or oceanic chemistry, and they often coincide with significant disruptions to biological systems. While all of the known examples can be explained by natural processes, Schmidt and Frank argued that similar patterns might result from industrial civilizations that rose and fell over relatively brief periods. The key insight of their analysis was that the signatures of ancient civilizations wouldn't necessarily look like human signatures. Different species might use different technologies, exploit different energy sources, and leave behind different chemical fingerprints. An aquatic civilization might alter ocean chemistry in ways that a terrestrial civilization wouldn't. A species that evolved in a different atmospheric composition might use energy sources that we haven't considered. This flexibility in the types of signatures to look for actually makes the search more challenging, not easier. If we knew exactly what to look for, we could design specific tests and surveys. But if ancient civilizations might have used technologies we can't imagine, then we need to cast a much wider net, looking for any anomalous patterns that can't be easily explained by known natural processes. The researchers also grappled with the question of duration. How long would a civilization need to last to leave detectable traces in the geological record? The answer depends partly on the intensity of their activities and partly on the preservation conditions where those activities occurred. A brief but intense period of industrial activity might leave a sharper signal than a long period of more sustainable technology use. Our own civilization provides a useful calibration point. We've been significantly altering global systems for only about 200 years, but our signatures are already clearly visible and will likely remain detectable for thousands or even millions of years. This suggests that even relatively brief civilizations could leave lasting traces if their activities were sufficiently intensive. But the analysis also revealed the limitations of the geological record as an archive of past civilizations. Most of the signatures we're creating today are chemical rather than physical. They depend on measuring subtle changes in isotope ratios, trace element concentrations, and the presence of synthetic compounds. These measurements require sophisticated analytical techniques that can distinguish between very small differences in composition. The further back in time we look, the more these signatures become degraded by geological processes. Rocks get heated and compressed, altering their chemical composition. Groundwater dissolves and redistributes elements. Erosion mixes materials from different time periods. The pristine chemical signatures that would clearly indicate industrial activity become increasingly difficult to detect and interpret as they age. This degradation effect means that evidence for very ancient civilizations would likely be much more ambiguous than evidence for recent ones. Instead of clear, unambiguous signatures, we might find only statistical anomalies, patterns that are suggestive but not conclusive. The older the putative civilization, the more careful we would need to be about distinguishing between genuine signals and natural variations or measurement artifacts. Schmidt and Frank concluded their analysis with a sobering assessment. Detecting ancient industrial civilizations in the geological record would be extremely difficult, and proving their existence would be even harder. The signatures would be subtle, ambiguous, and easily confused with natural processes, but they also argued that the search was worthwhile, not because it was likely to find ancient civilizations, but because it would help us better understand our own impact on the planet and the long-term consequences of industrial activity. Their work transformed the Silurian hypothesis from a thought experiment into a research program. By providing a rigorous framework for thinking about what ancient technological signatures might look like, they opened the door for other researchers to begin systematic searches for such evidence. The hypothesis became a lens through which to view the geological record, looking for patterns that might have been overlooked or misinterpreted. The implications extend beyond the search for ancient civilizations. If we can develop better methods for detecting technological signatures in the geological record, we can also better understand the long-term consequences of our own activities and make more informed decisions about sustainable development and environmental protection. The implications extend beyond the search for ancient civilizations, reaching into how we understand our own fleeting moment on this planet. And to truly grasp why detecting ancient technological signatures is so challenging, we need to confront an uncomfortable truth about permanence. Everything we consider solid and enduring, from our greatest monuments to our sprawling cities, exists in a constant state of decay from the moment it's created. The forces of destruction are always at work, patient and inexorable, gradually reclaiming every human achievement. This process begins immediately and operates on multiple timescales simultaneously. Within hours of construction, a new building begins to weather. Rain seeps into microscopic cracks in concrete. Freeze-thaw cycles gradually expand those cracks, and chemical reactions slowly break down the binding agents that hold the structure together. Paint fades and peels under ultraviolet radiation. Metal components begin to oxidize. Even the most carefully engineered structures require constant maintenance to prevent their inevitable deterioration. Without that maintenance, decay accelerates rapidly. Roofs leak, allowing water to penetrate walls and floors. Foundations shift as soil settles and frost heaves. Vegetation takes hold in gutters and cracks, its roots gradually prying apart masonry and pavement. Within a few decades of abandonment, even substantial buildings can become ruins. Within a century or two, they may be reduced to scattered rubble, their original forms barely recognizable. We can see this process at work in places like Chernobyl, where the exclusion zone created by the nuclear accident has become an unintentional experiment in what happens when human infrastructure is abandoned. 37 years after the disaster, the evacuated city of Pripyat is being steadily reclaimed by nature. Trees grow through the floors of apartment buildings. Vines cover the walls of schools and hospitals. The famous Ferris wheel, once a symbol of Soviet prosperity, now stands as a rusted monument to the temporary nature of human achievement. But Chernobyl represents only the very beginning of this process. On geological timescales, even the most dramatic human modifications to the landscape are temporary features. The Panama Canal, one of the greatest engineering achievements of the 20th century, would likely be unrecognizable within a few thousand years if left unmaintained. Erosion would widen and deepen the channel, landslides would alter its course, and sedimentation would gradually fill in sections of the waterway. Cities present an even more complex case. Urban areas concentrate vast amounts of material in relatively small spaces, creating artificial hills of concrete, steel, and glass. But these concentrations also make cities vulnerable to the forces of decay. Underground utilities corrode and collapse, undermining surface structures. Stormwater systems fail, leading to flooding and erosion. The very density that makes cities functional also makes them fragile when maintenance stops. Archaeological evidence from abandoned cities throughout history shows how quickly urban areas can disappear. Angkor, once the capital of the Khmer Empire and one of the largest cities in the medieval world, was largely reclaimed by jungle within a few centuries of its abandonment. Many of its temples and palaces are now barely visible beneath thick vegetation, their stone blocks displaced by the roots of massive trees. Without constant archaeological work to clear and maintain the site, most of Angkor would vanish entirely within a few more centuries. Even more dramatic is the fate of cities that have been covered by volcanic ash or sediment. Pompeii and Herculaneum, preserved by the eruption of Mount Vesuvius, give us a snapshot of what can happen when burial occurs rapidly. But they also show how fragile preservation can be. The organic materials, wood, leather, fabric, that made up most of the daily life of these cities had already decayed by the time archaeologists uncovered them. What remains are mostly stone structures and the hollow spaces where organic materials once existed. This pattern of preservation and decay has profound implications for how we think about the archaeological record. The materials that survive are not necessarily the materials that were most important to the people who created them. Stone and ceramic vessels survive while the food they contained disappears. Metal tools survive while the wooden handles that made them useful decay. Coins survive while the economic systems they represented collapse and are forgotten. The bias toward durable materials creates a distorted picture of past civilizations. We know much more about the monumental architecture of ancient Egypt than we do about the daily lives of ordinary Egyptians because temples and tombs were built to last, while houses and workshops were not. Similarly, we have abundant evidence of Roman military equipment because it was made of durable metals, but we know much less about Roman textiles because fabric rarely survives more than a few centuries. This preservation bias becomes even more pronounced when we consider much older time periods. The archaeological record becomes increasingly fragmentary as we look further back in time, not just because there's been more time for decay, but because the materials and construction techniques used by earlier peoples were often less durable. The earliest human tools were made of wood and stone, and while stone tools can survive for millions of years under the right conditions, wooden tools almost never do. The implications for detecting ancient civilizations are sobering. If a technological species had existed tens of millions of years ago, almost all of their physical artifacts would have disappeared completely. Their cities would have crumbled and been eroded away. Their tools would have corroded or decomposed. Their art and writing would have vanished without a trace. Only under the most exceptional circumstances would any recognizable artifacts survive. But the absence of artifacts doesn't necessarily mean the absence of influence. Even after all traces of a civilization's material culture have disappeared, its impact on the environment might still be detectable. Large-scale mining operations, for example, create distinctive geological formations that can survive long after the mines themselves have been forgotten. Quarries leave characteristic patterns of excavation. Slag heaps from metal smelting operations contain unusual concentrations of elements that don't occur naturally in such combinations. Agricultural activities also leave lasting environmental signatures. Large-scale farming alters soil chemistry, introduces non-native plant species, and changes erosion patterns in ways that can be detected thousands of years later. The Amazon rainforest, long thought to be largely pristine, is now known to have been significantly modified by indigenous peoples over thousands of years. Their agricultural practices created patches of unusually fertile soil called terra preta that still support different plant communities than the surrounding forest. Even more subtle activities can have long-lasting consequences. The burning of vegetation, whether for agriculture, hunting, or fuel, releases characteristic chemical signatures that can be preserved in sediment cores and ice cores. Changes in the composition of lake sediments can reveal alterations in the surrounding watershed that occurred thousands of years earlier. Pollen preserved in these sediments can show which plant species were present at different times, revealing human influences on local ecosystems. These environmental signatures have the advantage of being more dispersed and therefore more likely to be preserved than concentrated artifacts. While a city might be completely destroyed by erosion, the chemical evidence of its existence might be scattered across a wide area in soils, sediments, and groundwater. This distributed preservation increases the chances that some traces would survive even very long periods of geological activity, but it also makes the signatures much harder to detect and interpret. Environmental changes can have many causes, and distinguishing between human and natural influences requires careful analysis of multiple lines of evidence. Climate fluctuations, volcanic eruptions, and other natural processes can produce environmental changes that look very similar to those caused by human activities. The challenge becomes even greater when we consider the possibility of ancient civilizations that use technologies we don't understand or can't imagine. Our search strategies are necessarily based on our own experience of what technological signatures look like. We look for evidence of mining because we mine. We look for evidence of fossil fuel burning because we burn fossil fuels. We look for synthetic materials because we create synthetic materials. But there's no reason to assume that all technological species would follow the same developmental path. An aquatic civilization might develop biotechnology instead of metallurgy. A species with different sensory capabilities might create technologies based on principles we haven't discovered. A civilization that arose in a different atmospheric composition might use energy sources that leave no traces we would recognize. This uncertainty about what ancient technologies might have looked like makes the search for their signatures extraordinarily difficult. We're looking for evidence of something we can't define, using detection methods that might not be sensitive to the types of traces such technologies would leave behind. It's like trying to solve a puzzle when we don't know what the picture is supposed to look like and we're not sure we have all the pieces. The problem is compounded by the sheer volume of the geological record and the relatively small scale on which human activities typically occur. Even our most dramatic modifications to the landscape are tiny compared to the forces that shape the planet over geological time. The largest open-pit mines are dwarfed by natural features like river valleys and mountain ranges. Our cities, impressive as they seem to us, occupy a minuscule fraction of the Earth's surface. This scale mismatch means that evidence of ancient civilizations might be preserved only in very specific locations and might be easily overlooked in surveys that focus on broader geological patterns. A future geologist studying the rock record of our era might easily miss the signatures of human activity if they weren't looking in exactly the right places with exactly the right techniques. The search for ancient technological signatures thus requires a combination of broad geological surveys to identify potential signals and detailed analysis of specific sites where preservation might have occurred. It's a process that demands both patience and luck, and even then, the results might be ambiguous enough to fuel decades of scientific debate. The search for ancient technological signatures thus requires a combination of broad geological surveys and detailed analysis. But even then, we face a fundamental problem that goes to the heart of how we understand the past. The fossil record, which forms the backbone of our knowledge about ancient life on Earth, is riddled with gaps and biases that make it an unreliable witness to the full story of what once existed on our planet. When most people think of fossils, they picture perfectly preserved dinosaur skeletons displayed in museums, complete specimens that tell clear stories about ancient life. But these museum displays represent only the tiniest fraction of organisms that have ever lived, and they create a misleading impression about how preservation actually works. The reality is that fossilization is an extraordinarily rare event that requires a very specific sequence of conditions to occur. For an organism to become a fossil, it must first avoid the usual fate of most dead things, complete decomposition or consumption by scavengers. This typically means rapid burial in sediment that protects the remains from oxygen and bacterial decay. But burial alone isn't enough. The sediment must also contain the right chemical conditions to allow minerals to gradually replace the organic tissues, turning bone and shell into stone while preserving their structure. Even then, the newly formed fossil isn't guaranteed to survive. The rock containing it must avoid being heated or compressed enough to destroy its internal structure. It must escape chemical weathering that could dissolve the mineralized remains. It must be uplifted and exposed at exactly the right time for human paleontologists to discover it before erosion destroys it. The entire process from death to discovery is so improbable that paleontologists estimate only a tiny fraction of all species that have ever lived appear in the fossil record we've discovered so far. This preservation bias creates systematic distortions in our understanding of ancient life. Marine organisms with hard shells are overrepresented in the fossil record because they lived in environments where rapid burial was common and because their shells provided a framework for mineralization. Terrestrial animals without hard parts are dramatically underrepresented because soft tissues almost never fossilize, and land environments are less favorable for preservation than marine ones. The temporal distribution of fossils is equally skewed. We have excellent fossil records from some time periods and locations where conditions favored preservation, but huge gaps exist where entire epochs are represented by only scattered fragments. The famous Cambrian explosion of complex life forms, for example, might be partly an artifact of preservation bias rather than a genuine evolutionary event, since earlier soft-bodied organisms would have left much fainter traces in the fossil record. These biases become even more pronounced when we consider the possibility of ancient intelligent species. Intelligence doesn't require hard body parts that fossilize easily. Many of the most intelligent animals on Earth today, octopi, dolphins, various birds, have relatively fragile skeletons that preserve poorly under most conditions. If an ancient species had achieved intelligence without developing durable shells or bones, they might be almost entirely absent from the fossil record regardless of how successful they were during their lifetime. The challenges multiply when we consider that intelligence often correlates with behavioral complexity that reduces the chances of fossilization. Intelligent animals tend to live in social groups that care for their dead, potentially removing bodies from environments where fossilization might occur. They may preferentially inhabit environments that are unfavorable for preservation, such as forests or caves where organic remains decompose rapidly. They might even develop cultural practices that actively prevent fossilization, such as cremation or sky burial. Moreover, if an ancient intelligent species had developed technology, that technology might have made them even less likely to appear in the fossil record. Tool use can extend lifespans and improve survival rates, potentially meaning that fewer individuals die in circumstances that might lead to fossilization. Advanced medical knowledge might have led to practices that prevented disease outbreaks that kill large numbers of individuals simultaneously, reducing the chances of mass mortality events that sometimes create rich fossil deposits. The question of body size adds another layer of complexity. Large animals are generally more likely to fossilize than small ones because their bones are more robust and their bodies create bigger disturbances in sediment when they're buried. But intelligence doesn't necessarily correlate with large body size. Many of the most intelligent animals today are relatively small, and there's no reason to assume that ancient intelligent species would have been giants. The fossil record also suffers from what paleontologists call the pull of the recent. Fossils from more recent time periods are more common and better preserved than those from the distant past, partly because there's been less time for them to be destroyed by geological processes, and partly because the rock formations containing them are more likely to be exposed at the surface where paleontologists can find them. This means that our knowledge of ancient life becomes increasingly fragmentary as we look further back in time. The geographic distribution of fossil discoveries introduces additional biases. Most paleontological work has been concentrated in regions with good exposures of sedimentary rocks and well-funded research institutions. Vast areas of the planet remain largely unexplored from a paleontological perspective, particularly in developing countries, remote regions, and areas covered by thick vegetation or urban development. An ancient civilization that existed primarily in regions that are now poorly sampled might be completely missing from the fossil record simply because no one has looked in the right places. Even when fossils are discovered, they must be recognized as significant and properly interpreted. Many important fossils have sat in museum collections for decades before being recognized for what they truly represent. The first Archaeopteryx specimen, now considered one of the most important fossils for understanding the evolution of birds, was initially misidentified as a pterosaur. If fossils of obviously intelligent behavior can be misinterpreted, how much more likely is it that subtle signs of ancient technology might be overlooked or misunderstood? The problem of recognition becomes particularly acute when we consider that we might not know what we're looking for. Archaeological interpretation relies heavily on comparison with known examples, but the evidence for an ancient non-human civilization might not resemble anything in our experience. Tools or artifacts created by a species with different anatomy, different sensory capabilities, or different environmental requirements might not be recognizable as artificial to human observers. This uncertainty extends to the question of what kinds of traces an intelligent species might leave behind in the first place. Human intelligence manifests itself in specific ways that reflect our particular evolutionary history and physical capabilities. We use tools because we have manipulative appendages. We build shelters because we lack natural protection from the elements. We create art and writing because we have advanced visual processing and symbolic reasoning abilities. But intelligence could evolve along very different trajectories. An aquatic intelligent species might develop biotechnology rather than metallurgy, manipulating living organisms instead of inorganic materials. Their tools might be modified sea creatures rather than shaped stones or metals. Such biological technology might leave no recognizable trace in the fossil record, especially if the organisms involved were soft-bodied and prone to rapid decomposition. A species that evolved in a different atmospheric composition might use chemical processes that we don't understand or haven't mastered. Their technology might be based on principles of physics or chemistry that we haven't discovered, leaving behind traces that we wouldn't recognize as artificial even if we found them. The assumption that all technology must resemble human technology is a form of bias that could blind us to evidence that's right in front of us. The temporal resolution of the fossil record presents yet another challenge. Even under the best circumstances, we can rarely date fossils more precisely than to within a few thousand years, and for very old specimens, the uncertainty can be millions of years. This means that we couldn't detect a civilization that rose and fell within a relatively brief period, geologically speaking. A species that achieved high intelligence, developed sophisticated technology, and then went extinct within a few 100,000 years might leave no detectable trace in the fossil record, not because they weren't significant, but because the resolution of our methods isn't fine enough to capture their brief existence. The chemical signatures that Schmidt and Frank identified as potential markers of ancient civilizations face similar challenges in the fossil record. While these signatures might persist longer than physical artifacts, they too can be degraded or obscured by geological processes over long periods of time. Chemical evidence must be carefully distinguished from similar signatures produced by natural processes, and this distinction becomes increasingly difficult as the evidence ages and becomes more ambiguous. The cumulative effect of all these biases and limitations is that the absence of evidence for ancient intelligent species in the fossil record cannot be taken as evidence that such species never existed. The record is simply too incomplete, too biased, and too coarse-grained to provide definitive answers about the existence of brief, localized, or technologically sophisticated civilizations in the distant past. This doesn't mean we should abandon scientific skepticism or accept wild claims without evidence. Rather, it suggests that we need to approach the question of ancient civilizations with appropriate humility about the limits of our knowledge and the reliability of our methods. The fossil record has revealed an amazing amount about the history of life on Earth, but it has also taught us that much of that history remains hidden from us, perhaps forever. The search for evidence of ancient civilizations thus requires us to look beyond the traditional fossil record to seek traces that might have survived in other forms or in other places. It's a search that demands both rigorous scientific methods and creative thinking about what kinds of evidence might exist and where it might be found. The search for evidence of ancient civilizations thus requires us to look beyond the traditional fossil record. But even when we expand our perspective to include chemical signatures and environmental markers, we encounter another formidable obstacle: the ocean itself. The seas that cover more than 70% of our planet's surface are not just barriers to exploration, but active agents of destruction that systematically erase evidence of past civilizations with patient, relentless efficiency. To understand why the ocean poses such a challenge to the preservation of ancient evidence, we need to appreciate the dynamic nature of marine environments. The popular image of the deep sea as a static, unchanging realm couldn't be further from the truth. Ocean waters are in constant motion, driven by temperature differences, salinity gradients, and the rotation of the Earth itself. These currents redistribute sediments, transport chemicals across vast distances, and create patterns of erosion and deposition that can obliterate traces of human activity within relatively short periods of time. Near the surface, wave action and tidal forces create an environment of constant mechanical stress that breaks down any materials not specifically designed to withstand marine conditions. Salt water is highly corrosive, particularly to metals, and the combination of salt, oxygen, and motion creates an environment that can reduce even robust structures to fragments within decades or centuries. The remains of historical shipwrecks demonstrate this process clearly. Wooden vessels typically survive only a few hundred years in marine environments before being reduced to scattered timbers, while metal ships corrode away even more rapidly. The chemical environment of seawater presents additional challenges to preservation. The ocean is not just salt water, but a complex solution containing dozens of different dissolved ions that participate in ongoing chemical reactions. These reactions can dissolve certain materials while precipitating others, gradually altering the composition of any objects or structures that remain submerged for extended periods. Even supposedly inert materials like ceramics and glass can be affected by long-term exposure to seawater chemistry. But perhaps the most significant factor in oceanic destruction is biological activity. The ocean teems with life, and much of that life makes a living by breaking down and consuming organic materials. Wood-boring mollusks can reduce massive timber structures to hollow shells within a few years. Bacteria and other microorganisms decompose organic matter with remarkable efficiency. Even inorganic materials can be affected by biological processes, as organisms use minerals for shell construction or create acidic conditions that accelerate chemical weathering. The deep ocean presents its own set of challenges for preservation. While the cold temperatures and low oxygen conditions found in abyssal depths can slow some forms of decay, they also create environments where different types of degradation processes dominate. The immense pressure found at great depths can crush or deform structures, while the constant rain of sediment from upper layers of the ocean gradually buries anything that settles on the seafloor. This sedimentation process might seem like it would aid preservation by protecting materials from further degradation, but it also makes detection nearly impossible. The deep ocean accumulates sediment at rates that vary widely depending on location and conditions, but even in areas where deposition is relatively slow, thousands of years' worth of accumulation can bury objects beyond the reach of current exploration technology. In areas with rapid sedimentation, such as river deltas or regions with high biological productivity, evidence could be buried under meters of sediment within centuries. The problem is compounded by the fact that most of the ocean floor has never been systematically explored at the level of detail that would be needed to detect artificial structures or objects. Our knowledge of the deep sea comes primarily from widely spaced sampling stations, side-scan sonar surveys that cover large areas at relatively low resolution, and a handful of detailed studies of specific sites. The vast majority of the ocean floor remains as mysterious to us as the surface of distant planets. Even when we do find unusual objects or formations on the ocean floor, interpretation can be extremely challenging. The marine environment creates natural structures that can closely resemble artificial constructions. Underwater landslides can create linear features that look like roads or walls. Biological processes can build structures with geometric regularity that appears designed. Mineral precipitation can create objects with smooth surfaces and regular shapes that seem manufactured. The problem of distinguishing natural from artificial origins becomes even more difficult when we consider how marine organisms modify their environments. Coral reefs create massive limestone structures with complex internal geometries. Some marine worms build extensive tube networks that can cover large areas of the seafloor. Certain types of bacteria can precipitate minerals in patterns that create surprisingly regular formations. Without additional context, it can be impossible to determine whether an unusual seafloor feature represents biological construction, geological processes, or artificial modification. The question of preservation becomes even more complex when we consider how sea levels have changed over geological time. During ice ages, sea levels can drop by more than 100 meters, exposing vast areas of continental shelf that are now underwater. Conversely, during warm periods, sea levels can rise, flooding coastal regions where ancient civilizations might have flourished. This means that evidence of ancient coastal settlements might now be buried under hundreds of meters of water and sediment, far beyond the reach of conventional archaeological techniques. The Mediterranean Sea provides a dramatic example of how changing sea levels can affect preservation. During the Messinian salinity crisis about 5.5 million years ago, the Mediterranean almost completely dried up, leaving behind a landscape of salt deposits and deep basins. When the Atlantic reconnected and refilled the basin, any evidence of life that might have existed on the exposed seafloor would have been buried under kilometers of water and sediment. While this event predates any plausible technological civilization, it illustrates how dramatically marine environments can change over geological time. Coastal regions where ancient civilizations would have been most likely to develop are particularly vulnerable to marine destruction. These areas experience the most intense wave action, the strongest tidal currents, and the most dynamic patterns of erosion and deposition. Storm surges can move enormous amounts of sediment and debris, burying or exposing archaeological sites unpredictably. Tsunamis can transport materials hundreds of kilometers from their original locations, making it nearly impossible to determine where they came from originally. The continental shelves, which are now submerged but were exposed during periods of lower sea level, represent some of the most promising areas for finding evidence of ancient coastal civilizations. However, these regions are also among the most difficult to explore archaeologically. The water depths involved, typically 50 to 200 meters, are too deep for conventional scuba diving, but too shallow for many deep-sea exploration tools. The strong currents and variable weather conditions that characterize many shelf environments make systematic survey work challenging and expensive. When underwater archaeological sites are discovered, they often provide tantalizing glimpses of what might be preserved in marine environments, but they also demonstrate the limitations of oceanic preservation. The ancient city of Herakleion, discovered in Abu Qir near Alexandria, Egypt, was submerged by earthquakes and sea level rise over 1,000 years ago. Despite being preserved underwater, the site shows extensive damage from marine processes. Statues are eroded and fragmented, buildings are collapsed and scattered, and organic materials have completely disappeared. Even more challenging is the question of detecting chemical signatures of ancient civilizations in marine sediments. While the ocean does preserve some chemical records of past environmental conditions, these records are complicated by the complex mixing processes that operate in marine systems. Ocean currents can transport chemical signals thousands of kilometers from their sources, while biological and chemical processes can alter or destroy the original signatures. Distinguishing between local and distant sources of chemical anomalies becomes extremely difficult, particularly when the signals are weak or ambiguous. The deep-sea sedimentary record does offer some advantages for preserving ancient environmental signatures. In abyssal plains far from continental margins, sedimentation rates are relatively slow and steady, creating detailed archives of changing conditions over millions of years. These sediments can preserve evidence of asteroid impacts, volcanic eruptions, and climate changes with remarkable fidelity. However, the resolution of these records is typically measured in thousands of years, making it difficult to detect brief events like the rise and fall of a technological civilization. Marine cores from these deep-sea sites have revealed evidence of rapid environmental changes that occurred over periods of centuries to millennia, much faster than typical geological processes, but potentially consistent with industrial activity. However, all of these events can be explained by natural processes such as volcanic outgassing, methane hydrate destabilization, or changes in ocean circulation patterns. Without additional evidence, it's impossible to determine whether any of these rapid changes might have been influenced by technological civilizations. The search for ancient civilizations in marine environments thus faces a fundamental paradox. The ocean is one of the most likely places for early civilizations to have developed, given the resources and transportation advantages provided by coastal and maritime environments. But it's also one of the least likely places for evidence of such civilizations to survive over geological time. The same processes that make marine environments attractive to living organisms also make them highly effective at destroying the traces those organisms leave behind. This doesn't mean that the search should be abandoned, but it does suggest that any evidence found in marine contexts is likely to be fragmentary, ambiguous, and difficult to interpret. The ocean may have swallowed entire civilizations without leaving any trace that we could recognize today. The ocean may have swallowed entire civilizations without leaving any trace that we could recognize today, but the land presents a different set of challenges and possibilities for preservation. While terrestrial environments avoid some of the destructive forces that make marine settings so hostile to long-term preservation, they introduce their own complex patterns of creation and destruction that can be equally effective at erasing evidence of ancient activity. The key to understanding terrestrial preservation lies in recognizing that the solid ground beneath our feet is anything but permanent. The Earth's surface is in constant motion, driven by forces operating on timescales that dwarf human experience. Tectonic plates drift across the mantle at rates measured in centimeters per year, but over millions of years, these seemingly insignificant movements can transport entire continents across the globe, reshape mountain ranges, and completely reconfigure the planet's geography. The process begins with weathering, the gradual breakdown of rocks and minerals through exposure to water, temperature changes, and chemical reactions. Rain falls on mountain peaks and slowly dissolves soluble minerals, creating slightly acidic solutions that can etch their way through even the hardest rocks. Freeze-thaw cycles crack open joints and fissures, allowing water to penetrate deeper into rock formations. Plant roots follow these cracks, expanding them further as they grow and decay. This weathered material doesn't simply disappear. Instead, it becomes part of an enormous recycling system that redistributes the Earth's surface materials across vast distances and time periods. Rivers carry dissolved minerals and rock fragments downstream, where they settle in lakes, floodplains, and eventually the ocean. Wind transports fine particles across continents, depositing them in new locations far from their origins. Glaciers scrape up enormous quantities of rock and soil, carrying them hundreds of kilometers before depositing them in moraines and outwash plains. Over geological time, these transported materials accumulate in thick layers that gradually compress and cement together to form new rocks. Sandstone forms from ancient beaches and river deposits. Limestone develops from the accumulated shells and skeletons of marine organisms. Shale results from compressed mud and clay that settled in quiet lake bottoms and shallow seas. These sedimentary rocks become the archives of Earth's history, preserving fossils, chemical signatures, and occasionally the traces of human activity. But even these seemingly permanent records are subject to further transformation. As sedimentary rocks are buried deeper beneath accumulating layers, they experience increasing pressure and temperature. Eventually, they may be heated and compressed enough to transform into metamorphic rocks, their original structures and contents altered beyond recognition. Limestone becomes marble, sandstone becomes quartzite, and shale becomes slate, their fossilized contents and chemical signatures largely destroyed in the process. The most extreme transformation occurs when rocks are heated enough to melt completely, forming magma that eventually cools to become igneous rock. This process erases all trace of the rock's previous history, recycling its materials back into the Earth's crust in entirely new forms. The cycle can then begin again as the new igneous rocks are exposed to weathering and erosion, starting another round of breakdown, transport, and deposition. This constant recycling means that very little of the Earth's surface is truly ancient. Most of the rocks we see today formed within the last few 100 million years, and the oldest surface rocks date back only about 4 billion years, despite the planet being 4.5 billion years old. The intervening 500 million years of history have been almost completely erased by geological processes, leaving only fragmentary traces in the most stable and protected locations. For ancient civilizations, this presents both challenges and opportunities. On one hand, the vast majority of any physical evidence they might have left behind would have been destroyed by erosion, burial, and metamorphism over geological time. Cities would have crumbled, artifacts would have been scattered and ground to dust, and even the largest monuments would have been worn away by wind and water. The pyramids of Giza, impressive as they are, show clear signs of weathering after only a few thousand years of exposure. On the other hand, the same processes that destroy evidence can also preserve it under specific circumstances. Rapid burial can protect organic materials and artificial structures from decay, creating time capsules that survive for thousands or even millions of years. Volcanic ash, flood deposits, and landslides can bury entire settlements so quickly that they're preserved almost intact, like the Roman cities of Pompeii and Herculaneum. The key factors for preservation are the speed of burial and the stability of the environment where burial occurs. Materials that are buried quickly in oxygen-poor conditions can avoid the bacterial decay that normally destroys organic matter within years or decades. If they're also protected from groundwater flow, chemical weathering, and physical disturbance, they can survive for remarkably long periods. However, preservation sites with these ideal characteristics are relatively rare and tend to be localized. Most of the Earth's surface experiences continuous disturbance from erosion, soil formation, and biological activity. Even supposedly stable areas can be affected by climate changes, shifts in drainage patterns, or tectonic movements that expose previously protected deposits to destructive processes. The search for evidence of ancient civilizations on land thus becomes a matter of identifying locations where favorable preservation conditions might have existed over geological time. These include certain types of sedimentary basins, especially those that have experienced continuous deposition without major interruptions. Ancient lake beds are particularly promising because they can accumulate fine-grained sediments that preserve delicate materials and chemical signatures with high resolution. Cave systems also offer potential preservation sites because they're protected from surface weathering and can maintain stable environmental conditions for long periods. Some caves contain sediment deposits that span hundreds of thousands or even millions of years, preserving detailed records of changing environmental conditions and occasionally the remains of the organisms that lived in or near them. Desert regions, paradoxically, can also preserve ancient materials because the lack of water and vegetation reduces the rates of chemical and biological decay. The dry conditions that make deserts inhospitable to most life also slow down the processes that normally destroy organic materials and artificial structures. However, deserts also experience intense physical weathering from wind-blown sand and extreme temperature fluctuations, so preservation is far from guaranteed. The challenge of detecting ancient technological signatures in terrestrial environments is complicated by the sheer diversity of geological processes and environments. Unlike the relatively uniform conditions found in deep marine basins, land surfaces experience enormous variations in climate, topography, and geological activity. This variability means that evidence might be preserved in some locations while being completely destroyed in others, creating a patchy and incomplete record that's difficult to interpret. Natural processes can also create formations and deposits that closely resemble artificial structures or materials. Erosion can carve rocks into geometric shapes that look like walls, roads, or buildings. Mineral precipitation can create objects with smooth surfaces and regular forms that appear manufactured. Biological processes can concentrate certain elements or create layered deposits that might be mistaken for industrial waste or processed materials. The problem of distinguishing natural from artificial origins becomes particularly acute when dealing with very old potential evidence. The longer something has been exposed to geological processes, the more likely it is to have been modified or degraded in ways that obscure its original characteristics. A clearly artificial object might become so weathered and altered that it's indistinguishable from natural rock formations. Chemical signatures face similar challenges in terrestrial environments. While soil and sediment can preserve evidence of past industrial activity, they're also subject to mixing, leaching, and contamination that can alter or destroy the original signals. Groundwater flow can transport chemical signatures far from their sources or concentrate them in misleading ways. Agricultural activity, mining, and other modern human activities can introduce contamination that masks or mimics ancient signatures. Despite these challenges, terrestrial environments offer certain advantages over marine ones for preserving technological signatures. The greater environmental stability of some land areas means that preservation conditions can persist for longer periods. The accessibility of land surfaces makes systematic survey and sampling much more feasible than in deep marine environments, and the diversity of terrestrial environments increases the chances that some evidence might survive even if most is destroyed. Recent advances in analytical techniques have also improved our ability to detect subtle chemical signatures in terrestrial deposits. High-resolution mass spectrometry can identify trace quantities of synthetic compounds or unusual element concentrations that might indicate industrial activity. Isotope analysis can reveal changes in atmospheric composition or biogeochemical cycles that might reflect technological influences on the environment. However, the interpretation of these chemical signals remains extremely challenging, particularly for very old deposits. The further back in time we look, the more likely it becomes that natural processes have modified or obscured any original technological signatures. Climate changes, volcanic eruptions, and other natural events can produce chemical anomalies that look similar to those that might be caused by industrial activity. The search for ancient civilizations in terrestrial environments thus requires a combination of broad-scale surveys to identify potential anomalies and detailed studies of specific sites where preservation might have occurred. It's a process that demands both sophisticated analytical techniques and careful consideration of the many natural processes that can mimic technological signatures. Even with these tools and approaches, the results are likely to remain ambiguous for the foreseeable future. The terrestrial record of ancient technological activity, if it exists at all, is probably too fragmentary and degraded to provide unambiguous evidence of its artificial origin. Like the marine record, the land may have erased most traces of ancient civilizations, leaving behind only faint chemical echoes that are difficult to distinguish from the background noise of natural processes. The cumulative effect of both marine and terrestrial destruction processes suggests that any evidence of ancient civilizations that has survived to the present day is likely to be subtle, widely scattered, and highly ambiguous in its interpretation. The cumulative effect of both marine and terrestrial destruction processes suggests that any evidence of ancient civilizations that has survived to the present day is likely to be subtle, widely scattered, and highly ambiguous in its interpretation. This realization leads us to a deeper question about the nature of evidence itself. What would we consider convincing proof of an ancient technological civilization? And how might we recognize it when conventional archaeological approaches seem inadequate? The challenge becomes particularly acute when we consider anomalies that already exist in the geological record, unusual formations and chemical signatures that have puzzled scientists for decades without receiving definitive explanations. These anomalies occupy a strange middle ground in scientific discourse, too interesting to ignore completely, yet too ambiguous to support strong conclusions. They sit quietly in the literature, awaiting either better explanatory frameworks or more sophisticated analytical techniques that might resolve their mysteries. Some of these anomalies take the form of unusual mineral formations found in contexts where they shouldn't naturally occur. Spherical or cylindrical objects discovered in rock layers millions of years old have occasionally been reported by miners and geologists, their regular shapes and smooth surfaces suggesting artificial origin to some observers. However, natural processes can also create surprisingly regular geometric forms. Concretions, formed by the precipitation of minerals in groundwater, can produce nearly perfect spheres. Geological deformation can create cylindrical structures through the folding and compression of rock layers. The famous Klerksdorp spheres, found in South African mines in rock formations dating to approximately 3 billion years ago, exemplify this interpretive challenge. These small grooved spheres initially attracted attention because of their apparent artificial characteristics: smooth surfaces, precise spherical shapes, and parallel grooves that seem too regular to be natural. However, detailed analysis has shown that they're most likely pyrophyllite concretions formed by natural mineral precipitation processes. The grooves result from the intersection of the spherical concretions with the layered structure of the surrounding rock. Similar interpretive difficulties arise with metallic objects occasionally reported from coal seams or other geological formations. The famous London Hammer, found embedded in rock in Texas, or the Salzburg Cube discovered in an Austrian coal mine, initially seemed to suggest the presence of manufactured objects in geological contexts predating human civilization. But careful analysis of these objects and their geological contexts has revealed more prosaic explanations involving recent contamination or misunderstanding of the surrounding rock formations. These cases illustrate a fundamental problem in evaluating potential evidence of ancient civilizations. The tendency for unusual discoveries to be interpreted through the lens of existing beliefs and expectations rather than subjected to rigorous scientific analysis. Objects that appear artificial to casual observers may have entirely natural origins that become apparent only through detailed study. Conversely, genuinely anomalous features might be dismissed as natural variations without receiving the scrutiny they deserve. The problem is compounded by the fact that we don't have a clear template for what artifacts from an ancient non-human civilization should look like. Archaeological interpretation typically relies on comparison with known examples, but evidence of pre-human technology would by definition be unlike anything in our experience. Materials, manufacturing techniques, and design principles could all be completely different from anything in the human technological repertoire. This uncertainty extends to chemical signatures as well. While Schmidt and Frank outlined potential geochemical markers of industrial activity, their analysis was necessarily based on the types of signatures that human industrial civilization produces. An ancient civilization that developed along different technological pathways might leave behind completely different chemical fingerprints that we wouldn't recognize as artificial. Consider the possibility of a civilization based on biotechnology rather than metallurgy and chemistry. Such a society might manipulate living organisms to create tools, structures, and energy systems, much as some researchers today are exploring the use of engineered bacteria for manufacturing and environmental remediation. The traces left by such a civilization might be primarily biological rather than mineral, and they might be much more difficult to distinguish from natural biological processes after millions of years of evolution and ecological change. Alternatively, an ancient civilization might have developed sustainable technologies that left minimal environmental footprints, either through deliberate design or as a result of resource constraints. Such a society might have achieved considerable sophistication while leaving behind only the faintest traces of their existence. The absence of obvious technological signatures might reflect successful adaptation to planetary limits rather than the absence of intelligence. The temporal resolution of geological dating methods creates another layer of ambiguity in interpreting potential evidence. Most techniques used to date very old materials have uncertainties measured in millions of years, making it impossible to determine whether anomalous features represent brief events or longer-term processes. A technological civilization that existed for only a few 100,000 years might be indistinguishable, using current dating methods, from a longer geological process that produced similar effects over millions of years. This dating uncertainty also makes it difficult to establish patterns or correlations between different pieces of potential evidence. If we found several anomalous chemical signatures in rocks from approximately the same age, we couldn't determine whether they represent a single coordinated event like industrial activity or coincidental natural processes occurring at different times within the uncertainty range of our dating methods. The geographic distribution of potential evidence presents additional challenges. Earth's surface has been extensively modified by tectonic activity, erosion, and sedimentation over geological time. Evidence that might once have been concentrated in specific locations has been scattered, buried, or destroyed by these processes. What remains might be so widely dispersed that it's difficult to recognize as part of a coherent pattern. Moreover, the most obvious places to look for evidence of ancient civilizations are often the places where preservation is least likely. Coastal regions, river valleys, and other areas favorable for the development of civilization are also subject to the most intense erosion and sedimentation. The stable geological formations where evidence is most likely to be preserved are often in locations that would have been less attractive to ancient civilizations. The search for chemical signatures faces the additional challenge of distinguishing ancient signals from modern contamination. Industrial activity over the past few centuries has dispersed synthetic chemicals and altered element ratios across much of the planet's surface. Groundwater flow, atmospheric transport, and biological processes continue to redistribute these modern signatures, potentially contaminating samples from much older geological formations. Even supposedly pristine samples from deep boreholes or remote locations can be affected by contamination introduced during drilling, sample collection, or laboratory analysis. The more sensitive our analytical techniques become, the more difficult it becomes to ensure that we're detecting genuine ancient signatures rather than trace contamination from modern sources. This contamination problem is particularly acute for organic compounds, which are among the most promising potential indicators of ancient biological or technological activity. Many synthetic organic compounds are now ubiquitous in the environment at trace levels, making it extremely difficult to determine whether their presence in old samples represents genuine preservation or recent contamination. The interpretation of isotopic signatures faces similar challenges. While changes in isotope ratios can provide powerful evidence of past environmental conditions or industrial activity, they can also be affected by post-depositional processes that alter the original signals. Groundwater flow, mineral precipitation and dissolution, and biological activity can all modify isotope ratios over time, potentially creating false signals or destroying genuine ones. Despite these formidable challenges, some researchers continue to search for anomalous patterns in the geological record that might represent traces of ancient technological activity. Advances in analytical chemistry and mass spectrometry have made it possible to detect increasingly subtle chemical signatures in very small samples. High-resolution dating techniques are improving our ability to correlate events across different locations and sample types. Computer modeling and statistical analysis tools are also helping researchers identify patterns in large datasets that might not be apparent from individual measurements. By comparing the chemical and isotopic signatures found in rocks of different ages, it may be possible to identify systematic changes that reflect industrial activity rather than natural processes. However, even the most sophisticated analytical techniques cannot overcome the fundamental problem of ambiguity in interpreting very old samples. The further back in time we look, the more likely it becomes that natural processes have modified or obscured any original signals. The geological record becomes increasingly noisy and incomplete, making it progressively more difficult to distinguish genuine anomalies from random variations. The search for evidence of ancient civilizations thus remains largely an exercise in negative results. While we cannot prove that such civilizations never existed, we also cannot point to any unambiguous evidence that they did. The anomalies that do exist in the geological record can all be explained with varying degrees of certainty by known natural processes. This doesn't necessarily mean that the search should be abandoned. Science progresses partly through the investigation of anomalies and unexplained phenomena, and some of the most important discoveries have come from pursuing seemingly unlikely possibilities. The techniques developed for searching for ancient technological signatures may also prove useful for understanding natural processes and improving our ability to detect subtle environmental changes. Moreover, the search itself has value in forcing us to think more carefully about the assumptions underlying our understanding of intelligence, technology, and planetary history. Whether or not ancient civilizations existed, the process of looking for them helps us better understand the long-term consequences of technological development and the challenges facing any intelligence trying to establish a lasting presence on a dynamic planet. The process of looking for ancient civilizations helps us better understand the long-term consequences of technological development, and perhaps nowhere is this understanding more crucial than when we turn the lens of deep time upon ourselves. If we want to truly comprehend what traces an ancient civilization might leave behind, we need to conduct a thought experiment that is both humbling and illuminating. Imagining what would remain of our own technological society if it suddenly vanished from the Earth. This exercise is more than academic speculation. By understanding how our own civilization would appear to future archaeologists millions of years hence, we gain insight into the kinds of signatures we should be looking for when searching for evidence of ancient predecessors. It also forces us to confront the startling fragility of everything we consider permanent and substantial about our world. Consider what would happen in the immediate aftermath of human disappearance. Within hours, automated systems would begin to fail as power plants shut down without human oversight. Traffic lights would go dark, air conditioning systems would stop running, and the constant hum of industrial activity that characterizes modern life would fall silent. But these immediate changes would be trivial compared to what would unfold over longer timescales. Within the first few years, the effects of abandonment would become dramatically visible. Buildings would begin to deteriorate as roofs leaked, foundations shifted, and maintenance systems failed. Plants would establish themselves in cracks in pavement and eventually break apart roads and sidewalks with their roots. Wild animals would move into urban areas, accelerating the process of decay through their nesting and feeding activities. The carefully maintained boundaries between human and natural spaces would begin to blur and eventually disappear entirely. After decades, even substantial structures would show severe degradation. Steel would rust, concrete would crack and spoil, and glass would shatter from thermal stress and impact damage. Wooden structures would rot or burn in naturally occurring fires. Only the most robust buildings, those constructed of stone or reinforced concrete, would remain recognizable, and even these would be extensively damaged and partially collapsed. The pace of decay would vary dramatically depending on climate and local conditions. In tropical environments, high temperatures, humidity, and intense biological activity would accelerate decomposition and structural failure. Temperate regions with freeze-thaw cycles would see rapid degradation from ice formation in cracks and joints. Even arid environments, while slowing some forms of decay, would subject structures to intense thermal stress and wind erosion. Within centuries, most above-ground traces of human civilization would be reduced to scattered rubble. The great cities that now seem so permanent would become unrecognizable mounds of debris, gradually being colonized by vegetation and integrated into natural landscapes. Archaeological evidence suggests this process has already played out many times in human history. Ancient cities that once housed hundreds of thousands of people are now represented only by subtle variations in soil chemistry and barely visible earthworks. But while surface structures would disappear relatively quickly, other traces of human activity would prove more durable. Underground infrastructure, including subway systems, utility tunnels, and building foundations, would survive much longer than surface construction. These buried structures would be protected from weathering and biological activity, though they would eventually succumb to groundwater infiltration and soil pressure. Mining operations would leave particularly long-lasting signatures. Open-pit mines would remain visible in the landscape for thousands of years, gradually filling with sediment and being colonized by vegetation, but retaining their characteristic bowl shape and altered geology. Underground mines would create voids that might persist for millions of years, potentially collapsing to create distinctive subsidence patterns on the surface. The chemical signatures of human industrial activity would prove even more persistent than physical structures. Our massive consumption of fossil fuels has altered the isotopic composition of carbon in the atmosphere in ways that are already being recorded in ice cores, tree rings, and sedimentary deposits. This chemical fingerprint will remain detectable for hundreds of thousands of years, providing clear evidence of large-scale combustion activities even after all physical traces of our civilization have disappeared. Similarly, the synthetic materials we've created will persist long after their original forms have degraded. Plastics will break down into increasingly small fragments but may never completely disappear from the environment. The chemical building blocks of these synthetic polymers don't occur naturally in significant quantities, so their presence in sedimentary deposits would provide clear evidence of industrial chemistry even millions of years in the future. The radioactive isotopes dispersed by nuclear testing and nuclear power generation represent another type of persistent signature. Some of these isotopes have half-lives measured in thousands or tens of thousands of years, meaning they will remain detectable in the environment long after their sources have been forgotten. The global distribution of these isotopes, carried by atmospheric circulation and ocean currents, creates a planet-wide marker of 20th and 21st century human activity. Our agricultural practices have also created chemical signatures that will persist for extended periods. The massive use of synthetic fertilizers has altered nitrogen isotope ratios in soils across much of the planet's agricultural regions. The introduction of non-native plant and animal species has permanently changed the genetic composition of ecosystems in ways that would be detectable to future biologists studying the evolutionary record. Perhaps most significantly, we are currently driving the sixth mass extinction in Earth's history, causing the disappearance of species at rates comparable to the great extinction events of the geological past. This biological signature would be clearly visible to future paleontologists as a sharp decline in biodiversity preserved in the fossil record, accompanied by the chemical signatures of climate change and industrial activity. However, the detectability of these signatures would depend heavily on where future investigators chose to look and what analytical techniques they employed. Many of our most dramatic impacts are concentrated in specific geographic regions or environmental settings. Future archaeologists focusing on the wrong areas or lacking the appropriate analytical tools might miss much of the evidence for our existence. The temporal resolution of geological dating would also affect the detectability of our civilization. From a future perspective, millions of years hence, our entire industrial period would be compressed into what appears to be an instantaneous event. The development from steam engines to nuclear power to digital technology would all appear to happen simultaneously, making it difficult to understand the progression of our technological development. The global scale of our impact distinguishes our civilization from most previous human societies, but it also creates interpretive challenges for future investigators. The chemical signatures of industrial activity are now so widespread that they might be difficult to distinguish from natural global processes. Climate change, ocean acidification, and species extinction could all be attributed to volcanic activity, asteroid impacts, or other natural catastrophes if the investigators lacked the conceptual framework to consider technological causes. The preservation of our most sophisticated technologies presents particular challenges. Digital information storage, which contains most of our detailed knowledge about science, technology, and culture, is extremely fragile and unlikely to survive more than a few decades without active maintenance. Hard drives fail, optical media degrades, and solid-state storage loses its charge over time. Even if the physical storage devices somehow survived, the complex software and hardware needed to read them would long since have been lost. Written records on paper would fare little better, as organic materials decompose rapidly in most environments. Stone carvings and metal inscriptions might survive longer, but even these would eventually succumb to weathering and erosion. The vast libraries and archives that preserve our accumulated knowledge would leave no trace that future archaeologists could decipher. Ironically, some of our least sophisticated artifacts might prove most durable. Simple pottery shards could survive for millions of years, as could some glass objects under the right conditions. These humble materials might be among the few unambiguous indicators of our technological capabilities, though they would provide little information about the complexity of our civilization. The distribution of our artifacts would also be highly uneven, both geographically and temporally. Urban areas contain enormous concentrations of manufactured materials, but they're also subject to intensive recycling and redevelopment that disperses and destroys archaeological evidence. Rural areas might preserve more intact samples of our material culture, but at much lower densities that would be difficult to detect through random sampling. The lesson from this thought experiment is sobering. Even our global, technologically advanced civilization would leave only faint and ambiguous traces in the geological record after millions of years. Future investigators might detect chemical evidence of industrial activity and biological disruption, but they would have great difficulty reconstructing the nature and capabilities of the civilization that caused these changes. This perspective fundamentally changes how we should think about the search for ancient civilizations. If our own technologically sophisticated global society would be difficult to detect after geological time periods, how much more challenging would it be to find evidence of earlier civilizations that might have been smaller in scale, shorter in duration, or based on different technological principles? The geological record's systematic bias toward preserving certain types of evidence while destroying others means that absence of evidence cannot be taken as evidence of absence. The silence of deep time may conceal entire civilizations that rose and fell without leaving traces we can currently recognize or interpret. This realization doesn't prove that ancient civilizations existed, but it does suggest that we should remain humble about the completeness of our knowledge regarding Earth's history. The planet we inhabit has been home to life for billions of years, and intelligence may have emerged and disappeared multiple times without leaving clear signatures in the rock record we can access today.